hardly any movement. The room is full, so we might as well get started. We're starting a workshop, 90 minutes in one go. No one's got scared. Well, too bad. Ferenc Spala and Zoltan Panczel, the two of us, will be holding this workshop. We both are involved in IT security, and we have some know-how because we work as advisors. We have many years of experience. Zoli has some 4-letter and 5-letter acronyms, and he's prouder of the 4-letter acronyms than the 5-letter ones. And he's reported lots of 0 DIs. So you will probably come across him on many websites, hopefully not the website of the Hungarian police force. So the first 45 minutes I will be moderating, and then Zoli will take over. Buffer overflow is the subject for the first part, and what it is and how it can be functionally understood. We're not starting from scratch, and yet it will be quite hard to squeeze that inside 90 minutes, and Zoli will focus on the hardcore subjects. It's in 3 parts. András Kabai will carry on from where we will leave off, and then Buherator will have Metasploit workshop. So if you get to like this, you will have plenty to do in the afternoon as well. And this unofficially distributed Windows version is SP2. We apologize to other than Hungarian speakers because it's in Hungarian. Nothing extra. Perl and Python are the environments, and there's a word processor and a debugger and a metaframe, which we will only use in passing. So any one of you could easily make an image for themselves like this. The very first slide is something we won't focus on. In order to exploit buffer overflow, we will have to find a vulnerable point in the program and make it crash. It would have been nice to have a workshop on this fuzzing. So I'm not going to deal with how to look for exploitable loopholes in applications. The starting point is we have an application and we understand that there is a weakness in it. And easier M to MP3 converter is the first application. And from somewhere in the Internet vulnerability databases, we understand that if we feed it 30,000 A letters in a file, it will crash. So let's see if we give it not A letters, but something else to make it crash. So about fuzzing, you will find further information using these links. The presentation and the whole video will also be mounted on the website, so you won't miss out on any of this. Why do we want to make the application crash? Because I'm malevolent and I want the application to crash because of my content rather than the programmed content. And if I can make an application crash by using 30,000 letters A, it may not be good for me, and it may not be appropriate for running my idea. First, I need to get into the memory my own program. Without that, I don't stand a chance. And also, the application control should be handed over. There's the instruction pointer, EIP. If I can take over the application so that the memory address of the next instruction should be reset to my shellcode, then that's great. Stack Overflow is the subject of the first part. Zoli is drawing. Well, we'll put on a Picasso during the workshop, and we'll talk about Stack Overflow at the beginning, and then we'll see what happens afterwards. And we'll skip through this. 2 registers are interesting. ESP, that points at the top of the stack, and you need some previous understanding of stacks and heaps. We will not describe that. And the EIP includes the instruction pointer, which will locate in the memory the next executable instruction. So we'll focus on that. ESP stack can be manipulated, and the EIP can also be. I'll skip through this very quickly. That's the entry level. That's the stack and heap data structure. All of you are supposed to know that. If you don't, you'll find out. Here's a much nicer slide, which I'll show you. What's the point of Stack Overflow? In the red and white frame part, you will see a very simple function, which is given a string type variable and a local variable, 128 bytes of memory allocated. And without any checks, the string of any length we get is copied over to this 128 long memory address. If I feed 30,000 bytes, the first 128 won't cause a problem, but the rest will fill up the memory areas. So Stack Overflow, very quickly in a nutshell, works like this. Here's the stack structure. After a function call, and the yellow part is the one to watch here, because if there's a function call, there's a stack frame, which is marked in yellow here. And if the parameters go into the stack one by one, and EIP is saved, because the application will have to remember where to return after running the function. And here's the EIP value as well. It's not so important for us right now. And the local variables go to the top of the stack. And what's the point of Stack Overflow? We've locked 128 bytes of memory, but if I give it a lot more data, then I overwrite the rest of the stack content, including the EIP value, which is very good for me, because once I've overwritten it, I can hand over control to the program code I've sent in. And to go from words to deeds, I'll show you something. We tried at least 3 times to make sure that things should gel without a problem, but of course I guarantee you that they won't be working now, even though it's the same virtual machine that you got as well. Now, on the desktop there's 2 directories, part 1 and part 2. Now the projector is quite weirdly set here. And part 1 is the interesting part. Easy 01 and Easy 9 pair scripts are included here, and we will use them with this very friendly Easy RM to MP3 converter. That's the latest version, latest release. We'll get it to run a calculator application for us. And the nature of the calculator is not that interesting, but you can certainly believe me that this application wasn't designed to run a calculator. Can you see from the back of the room, or should I zoom onto this? So first we focus on making the application crash. All we send in is a cache 01 RM to MP3. We feed 30,000 letters A into it. In order to avoid technical glitches, I made thorough preparations, and I want to make sure that this is working well. I drag and drop, and it's crashed. It brings up a debugger, which is the visible evidence that it's crashed. And you can beautifully see this, that EIP is overwritten with lots and lots of letters A. And that's the cause of the crash. If I manage to overwrite the EIP using letters A, I can feed different content as well. I hope you can see that somewhat. It's the stack in the debugger, lots and lots of letters A. The two criteria will be met. First of all, I can overwrite the EIP using A letters, and I use different content in a short while. And also I've found different memory areas, including my data in the stack. So if the EIP is overwritten, and if I replace the letters A with my own program code, then that will be great. All I need to make sure is that control is handed over. One small remark: if you miss out on any of these short parts, we've picked an example that you will find a full description of on the web. And there's a team called Coraline Team. I will give you the link at the end of the presentation. They have several pages of PDF documentation on this. So when you're back home and you've lost out on this one, you can still check it. I'd better find the part to override the EIP with. We sent in 30,000 letters A. They all went into the address, but where were the 4 bytes that overwrote the EIP? We'll have to find them. Well, we can use a trial and error, the fool's method, because let's say I will send in 5,000 letters A and 25,000 letters B. The only drawback is I have to restart the application. But, it's no pain, no gain. So I'm sending in the input, and now I see letters B, because the first 25,000 letters are not much use. It's only to make the application crash. And the second 25,000 bytes are of importance. So it's the second part of the action that I can play around with. And I can run a binary search and continue by having the samples, but this is not what I'm going to do now. Here's the Metasploit. It's a great tool on Metasploit, which is designed for this. It's called Bot10 Create. Pattern create, and if I say 5,000, it's going to generate a 5,000 character string, and it will turn it into a unique combination, so it will be able to give you the exact beginning and end of any 4-letter combinations. And of course, in the second 5,000 section, I'm going to feed this 5,000 byte passage, and I'm going to get the information out of Metasploit where the 4 byte string is located within the 5,000. It's not fast, but at least it's slow. So you watch for this. You write it on a piece of paper. If you're really old-fashioned, you copy it onto the clipboard, and then you will ask Metasploit where that character string is located. A pattern offset is a small tool, and you give it the pattern you saw in the register, and you tell it to look for the same information in the 5,000 string. And it will give you what I already prepared. It was at position 1064. That's where 6A42, the 4-character string is. Why is that good for me? Because I will know the exact position in all that garbage of the 4 letters to override the EIP with. Somewhere in the memory, I will feed a lot of letters A, but I certainly expect letters B in hex 42. And we'll also have letters C to insert our own code. Let's see if I'm right. Well, we're writing this exploit on the fly, and it's not a stable one. Sometimes it's working on and off, but hopefully it's going to work in the demo. You can see 424242 in the EIP. I'm very glad because it fulfills the first precondition. I have the 4 bytes location to override the EIP with. And then, of course, the next question is, well, what exact content to use for the EIP. But I already have the location, and I'm happy. I'm also happy that the letters C can be seen at the bottom, so the shellcode can also be inserted. Well, this is an ideal animal that we're working here. And this guy will give you the EIP location, and Zoli is going to describe a different example, but in this case we have a perfect guy that's very tame and very easy to manage. Now, going through the next step, let's put EIP aside. We've identified the location of the 4 letters, and we'll come up with the content. And in the stack we saw lots and lots of letters C. I sent in some 500, and we don't know which of the 500 were visible, so we try to narrow down for the shellcode, and whether I'm looking at the beginning, the middle, or end of my letter C. A simple trick. We include a character string at the beginning of the C string so that we can recognize it in the memory. And we should not skip this step, because we'll see that, again, easy RM to MP3 is a very handy tool, but there's a small trick. I'll drag and drop. It's running. Can you see it, by and large? D, E, F, G here. And you can certainly see that it doesn't start with 1, which means that the variable that I want to use my shellcode for has to be shifted, so it's not the first letter, but maybe from the 5th byte backwards. And that still is good. All we do is shift the whole string over by 4 bytes. We'll include 4 X's. It could be anything. We need 4 bytes for the shift. And unless we miscalculated something, then in the stack the first digit should be 1. Let's check. Whose pacemaker is about to crash? It's not that exciting, is it? And we're glad because the first digit is 1. We're halfway through toward meeting the second precondition. We need to insert our own code. We've done half because we've got the memory segment where I can send my own code into, and it will start as I want it to. Okay. Now your smile is getting bigger and bigger because it's increasingly evident that I will be able to crack this. Now these 4 letters make a difference here. That's the PEC function, but nothing to worry about. All we need is to include this memory content to the EIP. And where is this memory from? And 01B423A. How do I get this content? How do I know that that's exactly what I want to include? So let me explain. Our shellcode 1ABCD, etc. That's in the stack. That's at the top of the stack, to be exact. And that's. Let me ask you a test question. Zoli is leaving. I'm not happy. What should I tell the application if I want it to execute what I will send in, 1ABCD and so on? Use simple language to make sure that we understand. So in simple lingo, describe what I should say to the application. To the place where this code is. And where is my code? At the top of the stack. So I heard someone say, let's jump to the top of the stack. Very good. And I want my application code to jump up to the top of the stack. So how do we say in the assembly language to the top of the stack? So jump, certainly, and what? Unfortunately, without the mic, I'm not getting this. So. A tolmács elnézést kér, de a közbeszóló nem használ mikrofont, úgyhogy sajnos nem tudjuk tolmácsolni. Kérjük, hogy szóljanak mindenkinek, aki hozzászól, hogy használják. Well, I didn't fully get this point. I'm sorry, but that's it. Well, ESP contains the top of the stack, and if I tell the program to jump, well, jump ESP is the assembly language version of this. Now, let me ask you, why did I have this complicated memory address rather than jump ESP? And that's an advanced question.
That's true, but it's not an answer to my question. Why do I write an address here instead of ESP or something like indicating the top of the stack? In this form, it is not true. At that address, there is a jump ESP instruction, and then this memory address should be written in. It will be read out from this memory address, and then we get this instruction, which means that we should jump to the top of the to the stack. So the title of the address of the instruction is enough, and then we fetch the instruction, and then we jump to the top of the stack. How do I get this address? I got it from the debugger. There is a debugger feature here. It is a historic moment. We use the debugger to use this easy MP3, and quite simply, I'm just looking for an instruction jump ESP over this memory area. Just a simple search. In all of the modules, jump ESP instructions. It's easy to hack, just you should use the mouse click. It's like Hollywood, everything is flickering. We got quite a number of jump ESP, only you should look at the green lines. The big books say that we should find memory addresses from the application on DLE, because the Windows DLE may change from version to version. So the wise old books say that we should find the jump ESP among the application's instructions, and then we are lucky at this time. And if everything goes well, then we have the same memory address written in here. There is an important remark here. There is one thing we should be very careful about. 0 byte shouldn't be in it. 2 zeros shouldn't be next to one another. 1 0 indicates the termination of a string in each and every computer language. So we have a string with letter A's, and then we have shellcode at the end. And if there is a 0 byte somewhere, then it will be interpreted as an end of the string, and then it will be thrown away. This is a rule of thumb that should be followed in 99.9% of the cases. 2 zeros next to one another is something that we don't like. Okay. We just shoot it down. I'm really worrying about Zoli, because she should get back by now. Otherwise I wouldn't run this, because it won't do anything extra with which we can jump to the top of the stack. We can believe this. And I take a giant stride forward. in the EIP, which is the top of the stack, and then we should change the letter E's and A's into some shellcode, which really looks ugly, odious. How shall we get shellcodes? We don't write shellcodes. Some privileged people, the elite sector writes it, but normal people don't write it. Normal mortals don't write it. We can get it from the net. There are lots of shellcode database exploit, for example, or we can generate it with the Metaspoiled, and Balin's going to speak about Metaspoiled. Metaspoiled is a CISP level task. You should go on clicking, you should find a platform that you like, and more or less, in addition to giving specifying two parameters, then you will produce a very ugly sequence, and this is the shellcode. We don't crack programs because we don't want to run the computer over our victims, but these things are much more interesting. Zol is back. Thanks God. And then we check if it operates, if it functions. This is the most delicate part, because if it doesn't work, then everything can be thrown away. I'm a bit worried. Which one did I run? 9. In the morning, it was really working. There is no computer in the background, but let me just give a 9 again, specify a 9 again, it will just produce this file. That's it. It's breathing and running. Yeah, I was surprised that there were no hitches. So we wrote an exploit for the Easy Convert program, and then only our imagination is the limit and the sky is the limit. We shouldn't modify anything else but the shellcode. Only then is it true if it's really handy animal. If the shellcode is longer than the amount of space I have for storing it, that's one hitch. And then I will tell you what we can do. Or there are certain characters contained in it, because of it really won't run. But otherwise, we are happy that it's going to run and will be able to run. That was the simplest exploit writing method. We have a stack overflow, we have space for the shellcode to get in, and then we can run it with the help of a jump ESP. The basic principle wouldn't change. If somebody understands or has understood it so far, then there will be no more sucking afterwards. There will be a big sucking, but otherwise you will be able to understand it simply. If we understood how everything is overwritten, then we will be in a very good position. Okay. This is one thing I wanted to show to you, and the other thing is a Zoltan MP3 player. I think the latest version 1.0. It wasn't developed after 2006. It sounds very good because it seems to be the latest version that we are breaking or cracking. Otherwise, the rest is under development. Okay, let's go back to the slideshow. SCH-based exploits, or not only EIP can be buggered, but this is the structured exception handler, SEH, which is always given, put to the application. So exceptional cases, exception handlers Very important thing. Small window, which Microsoft sends us as program X by code as program, then we shoot some message to Microsoft. We have a very good diagram here showing what the situation is. It's even a nicer one than this. That's a nice color picture. We like it. The story goes like this. If there is an exception handling block, then in addition to the previous things, the stacker will also contain an exception registration record. Next, you see the arrows. It is 8 bytes in length all the time, 2 times 4 bytes. The first 4 bytes is a pointer to the next exception handling block, and the next byte is just a simple pointer to the code which must be executed in the case of an exception. If you wrote already exception handlers, then you know that it is put in a list, and if there is an exception, then the program check if this catch branch is applicable, and then they will move to this memory place, and the instruction found will be executed. Otherwise, it will be started from the beginning. The reason why it is interesting to us after Stack Overflow is that the exception handler frame written in red is in a very good place. Why? Because how did we make overflow before? How many more bytes did we squeeze in? We have to reserve more place for the local variable. You remember that we pushed down the stack before. It's under the local variables. If I push in more data into the stack, then I can push everything down to deeper levels in the stack. For which I have again a very nice diagram. What will be our goal? First of all, an exception would be desirable, but we don't always have the chance to have this exception. On the other hand, we should achieve that our shell code be used to jump the our control. In the case of an exception handler-based exploit, we will do two things. Current SC handler, exception handler will be the memory address will be rewritten that it should point at a pop-ret sequence which handles the stack. You will understand that later. And the other secondary advice is that we should push a memory address into the next pointer where our shell code is to be found. Exception comes, current SC handler is executed, pop-ret will pop up a second exception, and then we'll check where to go in the case of the exploit, and we'll carry out this instruction. And then it will point to my shell code, which will then be executed. More or less it will just look like this. Lots of letter A's all the time. And then something ugly will be written in here, that's the shell. And then pop-ret comes here. It's not surprising. We will look for pop-rets like we did look for jump ESP. And then no operations instructions will be written here. And then let's see how it works. The first doesn't do anything here. Yeah, it will just squeeze in 5,000 letter A's and we will see if the program will fail. Zoli, please don't go so far away. That's my message. So I have 50 minutes for this stand-up, otherwise I will just collapse. I was cheating, that was the final result. It was a little cheating. It cannot be that good. And it just spit out the icon without any debugger, but there is a very nice exception handler in it, written nicely. That's why we are going to write an exploit based on exception. But I would like to see the debugger, what happens. So I start the whole thing in the debugger. We start it. It loads in. We play. It dies. It's dead. We are not looking for EIP, but we are looking for SEH, the exception handler chain. And then we are a bit overjoyed because the SC handler starts with 4141, which are the code for letter A's. Then the same play goes as it did before. Out of these 3 to 4041 codes letter A's, we should find those bytes that we really need, pop ret, I think. We use the text editor. We check this long sequence, and then we check those 4 bytes that went down to the SE handler part. I won't show you this. It's not pop ret, but something else. And this is the moral summarized here. That's what we see in the SE handler. If we ask Metasploit afterwards on which byte it is within the character sequence generated by it, and it says 588. This is the solution. But there is a question. It means that I send 584 letter A's and then comes shellcode. Why do we have 584 here? And I really just give a glimpse of the solution you before. SC handler is the second 4 bytes of the 8 bytes. So what I could check in the debugger was the lower 4 bytes, but also the upper 4 bytes are in play, and that's why I subtract 4 and then send in the same number of letter A's. And then comes the next exception handler part, and then the programmer should be executed, and then we must send in the shellcode somehow because we would like to execute the shellcode. So this is more or less a running or runnable version. Let's try to run it. I always have to start it from the debugger, because when it fails, it will be in that silence. When it is dead, it's silence all over the battlefield. It died peacefully and silently, and then what we have, 42. These are the letter B's, 42, 42, 42. That's what I wanted to put in, the code of the letter B's. Before that there is a break instruction, but it doesn't matter anymore. Good. What do we know? We know, and this is a rule of thumb for SEH exploits. Instead of letter B's, I would like to write pop ret. And we can find a pop ret sequence with the debugger. This is the sequence we would like to find, 3 instructions. I checked some EISI instructions. This is a very frequent common instructions. This is the memory address. Everything is perfect. And from this memory address, there is only one thing that I should go, namely, let's go back to this number 4, how it dies in debugger. In the debugger, I'm clicking all over the place without any system. I hope it will improve. Sorry. Did I press it? No, didn't. It will be seen in a second. It looks very nice. It shows very nice. This is the memory address given or specified by pop progress sequence. So with this, if there is an exception, then this is the memory address where the whole thing will jump. And I have to do nothing else but I just shoot it down, and I have nothing else to do but that's an interesting species. It just simply says jump 6 bytes forward. It's a simple instruction. What is happening here? There is an exception arising, and then pop ret is executed. What does ret do? Returns. Just pop the top of the stack, and this instruction should be executed. Pop is double because 8 byte must be popped up. On the top of the stack we have the exception handler, and when it is executed there is a prologue of 8 bytes. This is how the routine, the exception handler routine operates. One pop takes off 4 bytes, the second pop takes the second 4 bytes, altogether 4 bytes is taken off or popped off from the top of the stack. And then this clever thing written by me here will be just read out by ret, and I jump 6 bytes forward. But why 6? Why 6? Let me help you. Here I give you some help, hint. Here I am. Here I stand, I can't do else. And this is where it is written. 669. We jump over the 2 pops, and what else do we jump over? And the 4 bytes being underneath. And this is my shellcode sitting here wickedly. And physically, I put it after the SC handler. This is the place where the shellcodes are. We always send in a string. What does this tune operation instruction? NOP, it doesn't do anything, it's just a no operation. To jump 6 bytes is given here. Why are there 2 knobs? 4 bytes must be there to be jumped over, and knobs won't harm anybody. The reason why I'm jumping 6 bytes, because we jump over 1 knob, second knob, another 4 bytes, and then the control is here.
And it can start running. If all goes well, when I have this run and I push that inside the MP3 player, it will give us this nice calculator. Well, shell operators look these very ugly animals, and lots of shell operators look very similar. In all of them, you will find, almost all of them, you will find these lines, whether it will jump 6 or 11, it depends on how it is structured. And here it says pop pop, and here's a shellcode. This one is a bit more convoluted, but lots of exploits are very similar, and lots of them will look like this.
Amit még ígértem, hogy mutatok linkeket, ezt én fölírnám, bár a szlájdok elérhetők lesznek.
Well, as I promised, coraline.be 8800. This has the PDF tutorial, and the website will also have the presentation. So even working at home, you can get ahead relying on this. And it's the first, second, and third parts. They end generally there, the SEH exploits. So you might as well check them out. And now we're switching roles. Are you bringing your laptop, or are you going to use this? Now we'll switch the floor quickly. What if you just showed us your slides on here? There are only 2 slides. I think you can quote them off the top of your head. Well, then bring your laptop over.
Elfelejtettem valamit.
I forgot something. It's a technical note. I'm an organizer again. Is there anyone who is a Czech colleague? Well, if there isn't any, then no problem.
Üdvözlök mindenkit!
Welcome everybody.
A második részt én fogom tartani, Panczel Zoltan vagyok.
I'm doing the second part. Zoltan Panczel is my name. I was asked to explain why I'm wearing these clothes. An American security expert was bored, and he identified 4 categories of other IT experts on security, and he says the ones writing exploits and such like security pimp is their cast. So I try to dress accordingly. I'm going to present 2 things to you. One thing we couldn't burn on the CD or the DVD because the basic system would have been 2 gigabytes. So one is an SAP product and an HP node manager product. Loophole is what I'm going to exploit. So first of all, the SAP product loophole has already been patched. So this is already history. At the ZDI site, there was an announcement that there was a security loophole in the product, so a simple advisory will turn into an exploit. I tested it beforehand, so in principle we should get a shell at the end. So the fundamental exploit will look like this. I'm using a trick here because I'm using backtrack and Windows. Windows is the same image you got on the CD or DVD. The reason I brought up this small screen, unfortunately fuzzing, we won't have enough time for that, but I'll explain quickly how you can spot the loophole. The announcement is at Shopmax DV. The loophole was in there, in security. It only says that port 7621, if you push lots of data inside, you can take over control of the register in the application. And I'll make a drawing about this, how you can easily find out. It's a freely available, downloadable tool from the internet, and there's no mic on the other side, so I'll have to shout. Now this is available for Linux and Windows. Unfortunately the sound level is very low, so it's going to be difficult to interpret this. And here's my Windows-based machine, and it's running software, and here's the Linux-based machine. And I can say that the client should not log on to the Windows or local host, but to this alternative, which will grab the packets and return them to the Windows interface, acting as a proxy. So all we need to do is, once we connect to the server, and then we take over the packets from the Windows client. And then we can identify byte by byte. There are tricks to fuzz them, long strings. And all we need to do is to use the Windows host running the database. If we run a debugger, we will wait for exceptions. That's a simple template, which is not yet filled in. It's also available on the CD. I left it in here because later on you will be able to use that to write other exploits. Thankfully, programmers can write code so that one template can lead to many subsequent exploits, to security loopholes. And in this codelet, you can see the Python code here. Just to mix Spala and Python here. Let's see what we could interfere with. Looking TELF and 66, we tried to fuzz in 00 and going through like that. And it jumps out in the debugger that if we start fuzzing this part, then Ferry mentioned this several times, our data will find their way into the EIP register. So all we need to do is to send that data to the target server. And of course, I'm using a gimmick because I have a stage 3 file here. And as you can see, there are 15,000 additional A's to make the application truly crash. And then the value here, that's capital A 41, 41, 41, 41. And this will be included in the EIP register. And if technology stays with us, so far it's not very much been with us. So if I run this stage 3 code here, it's using the same Windows you got on your CD or DVD. And if I select this port 7 to 10, and we let the application continue to run. Okay, this is what I was talking about. Just a second, I want the address. I'll get it and then we'll be okay. If I start this program, it no longer indicates an error. Within seconds, in principle, we should get a nice exception. And those nice numbers are gone with the other stuff. And you can see that EIP was overwritten using 41, 41, 41, 41 as a character string. If you paid attention to Ferry's presentation and if you understood what he was saying, you will very quickly discover what the major shortcoming of this is. We have a huge problem. Yes, that is the case. We don't see any A's in any of the registers or the stack at the bottom here. We don't see any memory address that would refer or point to that value. Why is that a problem? Why can it be a problem? Because our own code cannot run. So now we go back to the no frills method. It doesn't work everywhere. I'll ask at the end of my presentation to list at least 2 Windows distributions where this would not work. So I reopen the system because the service goes dead, because the debugger drags it down, and it's crashed anyway because it refers to an unavailable memory index, a memory address, where there is no meaningful data and there isn't even such a memory address, in fact. So how can we debug this? How can we include and where can we include our code? All we need to do is set a memory address as the return address to include a breakpoint. And then our system won't crash. It will rather halt, the debugger will halt it at a certain memory point. And then we can check the memory, because somewhere there must be lots of A's, except that there is no pointer pointing at the A's right now. And we can track that. So in a simple approach, we can give it an instruction to jump there. There's a nice tool. It's on the CD. It's also available in the desktop. It's the finejump.exe. Make sure you save it, because on the web it's very difficult to find. It's not easy to come by, and even the source is difficult to compile. So if you want to do such things, it's very useful. Now I need to specify the DLLs. Which DLLs? The DLLs associated with the program. Kernel 32 DLL is one example, but there are lots and lots of DLLs used by the applications. All we do is pick any operations. Jump ESP or call ESP is what I'm looking for, and this intelligent tool will give us the address. That's where the instruction is located. In principle, these addresses vary with the Windows version and service packs, even with the language. If you look at a Hungarian version or an English Windows XP service package 2, then in principle you should rewrite the code. But in this case, we've toppled the rule, because it was written for the English XP, and we'll be able to use that in the Hungarian SP. So there might be some tricks that Windows aren't disclosing to us. So let me now modify the exploit, which is working in principle, and I reset the address to return to. And I'll squeeze lots of information into this line. Let me highlight this. And the rest are commented out, except for the first one. Otherwise the server would throw the data away, because it would not be able to understand them. And as you can see, it was quite a fight to get this operational code together. What this is all about, I'll present it, but first let me show you how we can debug this exploit and how we can find the A's we sent in. I'll copy this small code snippet out, or excuse me, memory address. And again, I'll go back into the program. Immunity debug is the one I like, because it gives me the port numbers where the services are located, so I don't have to manually go out and look for them. Now again, I connect back to this application, and if all goes well, I'll enter this address, and you can really see call ESP. I double click, add a breakpoint, and then I will continue to run the application. And now here's the technical glitch again. If we start this, I hope you'll be able to see. Or not. Oops, sorry. I sent in the original, and this will be okay like this. So again, I repeated it. I can't really see the screen here, and I can't tilt the screen further back.
majd a megfelelő részt. És most látjuk, hogy ugye megjelent egy új kapcsolat, és ha visszalépünk a Linuxba, hogy egy kicsit változatosabb legyen a dolog, akkor egy, telnet parancsal.
Have a bit of variety here. Then at the address 150, I use telnet to get shell in.
It is run with administration authority, then it has admin or system authorization, which is the case in 99% of all cases. So much about this demo. Exploit, do you check the exploit DB page? The off-page security guard will get VW Milworm. If you take a look, this is where you can apply for a tester, and there is a very short description about the security error, and then you can form a team, and then you will be able to write an operational exploit for those who are interested in this kind of things. And now comes the demo, which didn't operate this morning, and then I modified it, and it worked even less, and I went back to the original state, and it started to operate all of a sudden. Unfortunately, it is not on the DVD, but it is downloadable from HP. The only huge problem which makes this software crackable is that who knows the network node manager of HP? Please raise your hand if you know this thing that I... There is one problem with this software. It should be able to have an insight into all parts of the network, otherwise it cannot manage and diagnose the devices. But if somebody cracks it, then firewalls and similar things just keep fall tumbling down, because with that IP address the network allows you to get in and get out, and if somebody tries to disable the office segment from being accessed, and they use monitor, or if we would like to monitor, then from this server we can crack it. Let me just show you a very rough exploit to you, which is not even ready yet. It is just in a semi-finished condition. Let me just explain to you, and you will see what it is all about. This is a real rock and roll situation, and you can spend countless or dreamless nights with it. The previous question: why could this exploit be operational on XP? Because we jump into the stack in a direct way. Just try to think of defense solutions. Yes, XP, SP2, the stack is always there, there's no randomization, and if we have Linux, and then it moves the stack from different memory places to all new different memory places, it will be always operational. But just give me 2 copies of Windows where it doesn't operate. On 6 and 7 it doesn't work. So if you put this application there, then luck plays an important and very hard part for us to solve it. We forgot to tell you that these things are not shown to you to write exploits and break into all kinds of systems, but it is an important part of IT security. This is the penetration testing part of IT security. It is a kind of vulnerability test, and the report where you work from your brain instead of using automated scanners and can understand errors like this. It's much superior to systems where there are only mechanical things. In outside Hungary, if somebody just breaks into a system in legal work, then reports should contain exploit codes that they have really used. The problem is not a kind of copy pasting from Milworm, but codes of your own development, and it shouldn't be like directly running it from the report, but we should go down to the level that it will override the register with letter A's, and from this we can take further steps. If we would like to crack a system, then they can do malicious things for the company. How much time do I have? No more time. Do you have? HP Network Node Manager has a corrected error, and this is the following. It is composed of several things. This is a big software with lots of smaller and larger applications. The larger the code is, the more opportunity for errors there are. It's a huge code, so the whole system will put on 2 gigabytes extra, and that's why I couldn't put it on the CD or DVD. I'll show you a part of the system with which you can diagnose certain things. It runs on the web. The problem is that it will be given 2 arguments, and the sum of the 2 arguments is bigger than a certain number, and there will be a buffer overflow, because it will copy the 2 arguments into a buffer. So he is expecting 200 from here, 200 for there, and then 400 will be enough. Input validation. Have you heard about input validation at the university? Have you heard of input validation? Put up your hands if you have heard at the university from input validation. Are you a teacher somewhere? I bet. And this is a big shortcoming of the developers, because you really can't hear much about input validation. 80% of security errors can be prevented by input validation, or even 90%. If the expected data is controlled. If I receive numbers, then I really get numbers. If I have 5 characters, then I should have a length of 5 characters. That's a web problem. Let's start at the beginning, and let's jump into the middle. Since it is a CGI, and UML is used to pass the shell code, for this reason it should have certain character restrictions. Those characters that cannot be printed on the web will not pass. What characters can we input into this program? I will just draw an URL, and then you will be able to imagine this kind of characters that we can input. Here is the flip chart. Take a look at this. But he's not using the microphone. Please tell him that the interpreter doesn't hear him at all and doesn't see him at all. Here we stop interpreting.
Is it possible to use microphones to translate?
It is impossible to translate because you don't have a mic. And we can't see what you are drawing at all. Okay, he will explain it later as soon as he writes it. Sorry. First I wrote it, and now I explain it. This is a typical URL, CG level. X is the attackable part. It is given a parameter, which is 1 now, so that we have space enough, and caps and it gets parameter b with the value of 2. You have seen URL till you type them in. What kind of characters can you specify under a URL? There is a special device with which we can produce papers with.
URL encoding, so it's a percent sign and then the actual digits for like the ASCII, sorry, the hexadecimal for the ASCII. For example, if you want to the Spanish, you use percentage.
Sorry, we can't hear this English. Yeah, he says printable characters, and he was really given the code region from a certain character to the last printable character. Printable characters can be sent in. Let me help you. What is the single character that should not be here, but it is on the figure? The only that cannot be here, but it's on the figure. And there is something cannot be here. I didn't understand that. 1, because it can be found in payload. The CGI script, which works according to HTL standard, then it will identify a beginning of a new parameters. The other big problem is that these CGI script, they receive the info in hexa, they execute it and jump out. It is impossible for us to debug because we have 1/1,000,000th of a second to grab it, so we have to do a little trick. And this is the SMNP viewer exe, if I understood it correctly, and that's where I can click. I don't know if you can see it. From the back we can't see it. The essence of the method is that I can influence the run of the program. I can rewrite the whole binary code. Every program has an entry point with a little environment, and they get started under certain rules and under certain parameters. This entry point can be hijacked. The program, there are certain spaces in the program, empty spaces, like here, filled with 0 zeros, and I grab the first instruction and I put a jump instruction that it should jump to my own code. You can follow the red strip which points to the end of the jump statement, and this is where we land. How can we get hold of the running of the program? A sleep is put in. We put a value into register. As far as I can see here, it is 15 seconds. We put it into a register, and we save the register onto the stack, and then we call kernel 32DL the sleep function, and as soon as sleep function is over, which take off the top data on the stack as time. This is 15 seconds, and the jump that we wrote ourselves, we jump back to the original entry point of the program, and then our code runs problem-free on. There are lots of cases like this. Slowly, quietly, with certain tranquility, we start our program. We just jump back to Windows, and from the debugger we jump over to this little binary part, and then let's see the sharp test if it really works. Thanks God. Service should be restarted because CGI always gets out because they are more intelligent species. Now let me show you what we can do instead. That was the program that either operated or didn't operate this morning, like in the fairy tales. If we check the running processes, then we won't see these exit things that I mentioned with underscore. We start the exploit, and among the running processes, at the very end. I try to be quick here at the very end. Here is my small program running, and it is now in the sleep phase, moving towards sleep phase. And if I let it run on, then I receive an exception immediately on the basis of what I told you before. What type of overflow is this? That's a question. Let me help you. This is an SEH overflow, exceptional handling overflow, and then here I can see my own instruction, pop ret, as it was shown by my colleague. And I use this genial built-in gadget of Windows, which may help us save our life, especially mine. I told this part that we should run on, and it stopped at the interrupt which I set, and from the interrupt we can take steps forward one by one, instruction by instruction. What is the problem here? What is obvious here to all of you? Yeah, you can see that there is an end to it. We cannot screw it down to infinity. We cannot put a share code because we have very limited space. In Linux it would be perfect, but in Windows 300 bytes are here, and if we must do some tricks, because only printable characters can be here, then it will go up to 700, 800, or even up to 1000. And there is only 70, 80, 100 bytes, no more space for the bytes. What else can we do here? This is the end of the stack, and there is nothing else at the bottom of the stack. So we allocate this much, and then here we are down at the bottom of the stack, and then I give one more step and the program dies. What can we do? Very sad jump things here. If we scroll it back, the debugger scroll back, then we can see that we have space here, space enough here. I already revealed what you should do. Any assembly code can be squeezed in, whatever I want. Just use your fantasy, use your own imagination. That's it, that's it. We try to jump back to where, what is the code of the jump? From Ferry's slide. Just take a look at the flip chart. No voice again. If you can read it, that's it. I can't. There are certain character restrictions, and this EP is, or EB is not, is a non-printable character. What else can we do instead? We use the tutorial manual with the hexa counterparts of the instruction codes, and then we will find those instructions that represent printable characters. With this semi-finished code, I wanted to help you. What is subtraction? Opcode SUB in assembly. Subtraction. Who learned assembly language here or wrote some code in assembly? Good, because this is an SUB subtraction instruction.
So all we do here is take the stack pointer, we save it to the stack so that we can use it, and then put it back into a register so that we can use it for operations. And since the SUB value to the A, and somebody has in front of them perhaps a hexadecimal table, you can see that this is a printable character. All we need to do is subtract off that value. And the SUB-EA hex, we use that as a register in which we subtract the values. And these are within definite character ranges. They must be printable, so we must subtract 3 times, which normally we could subtract in one go. And I can influence the content of this register in whatever way. And I can subtract from it, since the stack is pointing here. On the left, it's black. That's where the program run is at. If we subtract, we get where? We subtract 5,000, we go up. We go back to the lots of A's, where there is space, and we can include payload. And then what we do is put that into the stack and pop ESP. We issue the command to overwrite the ESP value and jump ESP. The code will make a jump to that code snippet. And if all goes well, our code will run. The only thing to watch out for, I wonder who's used Metasploit to generate shell programs. None of you? No one? Then go back and check. You can generate all sorts of shell codes very easily, and thankfully smarter people than us already wrote that part, so we don't have to spend days and weeks. It will produce printable characters. All you need to do is include that in your template, and then the code will work. Well, those in doubt can continue to use the egg hunter, as in the previous example. And since we're at HTTP, in the user agent or whatever, we can include our shellcode. And it's enough to include our egg hunter, 32 bytes. How much here? A bit more, because it must be converted, because it also includes non-printing characters. Have you got the figure? Nods or shakes? Then I will tell you once again, good, thank you. And after Egg Hunter has done its run, the user string will be placed in memory, Egg Hunter will find it, and our code will run. And this NNM is a tricky one, because thread management is incredible, and they will crisscross memory areas. There are exploits that will work for a minute and then automatically will terminate because another thread will write into the shellcode section. So you should test doing this when you have a bit of experience writing shellcode exploits. And the nice way to go about this would be to start in the morning and finish off in the evening. And then I could have checked whether everyone was with me and whether they were doing things all right. And now let's just check if this code, if all is true and well, then you can find that on the DVD. Yes, you can download it. Yes, that's the one. Thanks. Feel free to test it, experiment with it. Well, I don't know how to program in assembly, but this one takes very little knowledge, mostly about the programming structure, and we live in a comfortable age. Almost everything is available on the web. So there are very few problems left for which there is no solution or help available. So we've run out of time. Thank you very much for staying with us and for your perseverance. And if you have any questions to ask of me, maybe not tomorrow, but Ferry certainly will be here, and I'm available throughout the day, and you're all kindly invited to the evening party, because those of you who want to miss it don't know what they will miss. Thank you.